Welcome, everyone. Thank you for joining us for today's webinar. This webinar is going to be a bit different as we really want to encourage interaction and discussion. So if you would like to be unmuted at any point to join the conversation, please just click the raise hand or send a chat message to the organizers, and we will unmute you so that you can either ask your question or join the conversation. You can also write your question into the question box, and our presenter will be checking that throughout the presentation so that conversation can take place as the presentation unfolds. So we really encourage your questions and your interactivity. Thank you again for joining us. And with that, I'm going to turn it over to Arain Mullins for the introduction.
Thank you, Amy. Welcome, everyone. My name is Arain Mullins. I'm working with Desmet Balestra out of our North American offices in Georgia. Thank you for joining us today for the Deodorization Explained and Myth Exposed. Today's webinar is presented by Alan Paine. Alan was born in England and studied chemical engineering at the University of Surrey in Guildford. In 1984, he joined the Rosedowns Company, which is now part of the Desmet Balestra Group. In his career, Alan has taken various roles, mainly associated with the vegetable oil refining, including 5 years working with Desmet Balestra in our North American offices. Today, he lives back in England and has recently retired from work as global technical support on behalf of Desmet Balestra's office in Brussels, Belgium. He's a regular contributor to the AOCS Inform Connect forum. Away from work, Alan's interests include amateur theater, music, and writing. Together with a group of 8 other writers, he has brought out a collection of linked science fiction stories available online as ebook or paperback. Please write any questions for our presenter into the question section of your control panel. All questions will be addressed at the conclusion of the presentation, but we will also try to answer questions as they pop up. So please type those questions in. Thanks again for joining us, and with that, I'm going to turn it over to Alan.
Thanks very much, Arain. I hope you can see the first slide that I've prepared here. Now, deodorization, you might say in some ways it's a fairly simple process. Certainly the principle is quite straightforward. We heat the oil maybe to a temperature of around 250 degrees Celsius, expose it to a pressure of a few millibar, and then we blow steam through the oil to remove any volatile substances such as smells and fatty acids and various other things that we want to take away. But it's important to do that in the most efficient way possible. And there are some misconceptions around deodorization, and even, dare I say it, some myths. Now, obviously, you want to challenge some of the things I'm saying. You think, well, I haven't quite got that right, or there's another angle, then please let me know. So first of all, just let's remember that vegetable oil is something that's been around a long time. The olive trees of Crete are thousands of years old, and elsewhere in the Mediterranean region. And olive oil was widely traded in Roman times and before in clay jars like these ones that were excavated from Herculaneum, which was destroyed in 79 AD along with Pompeii. Perhaps a slight misconception is that the vegetable oil industry and vegetable oil processing is older than the 20th century. It's easy to think, well, nothing really happened much before the 20th century. This painting by Cornelius de Man of a whale oil refinery in Jan Mayen Island, dating to 1639, is an interesting one. Cornelius de Man didn't actually go there, and in fact it's way out in the Arctic Ocean and quite difficult to visit even today. But the painting probably reflects the industry that the man saw around him in the 1600s. And we've also got to give a little bit of insight into British patents that also tell us something about how oil was processed hundreds of years before today. Now I see a question here, deodorizing without degumming. I think no, well, yeah, what I'd say about deodorizing without degumming is really you've got to get the phosphorus level of the oil down to some degree, and if you didn't remove the enough phospholipids, phosphorus from the oil, then they would all char inside the deodorizer, and you wouldn't be in good shape at all. I don't know whether you want to come back on that, but we'll move on here now. Around the beginning of the 20th century, someone had the idea that deodorizing under vacuum was going to be more effective than sort of previous processes. So what we've got here is a simple system. You put a batch of oil in the deodorizer and you heat it up, blow some steam through, and the oil is deodorized. Now, the conditions for doing that are relatively mild compared to what we think of today. We'd have 180 to 190 degrees Celsius here. 6 millimeters of mercury was very common, about 8 millibar, and 65 kilos per ton of steam injections. That means we're putting 65 kilos of steam into the oil for every ton. So, and this is a very large quantity by modern standards. And the problem with batch processing like this is that it's not just that it's a very low production rate. You might only do 10 or 20 tons maybe per batch, maybe 3 or 4 batches a day, but it's very, very expensive. You're using a lot of steam injection, there's no heat recovery, so overall and you've got a lot of steam that has to be handled by the vacuum set, so you need a very big vacuum set, very large heating. It's a very inefficient process, but the quality of oil you can produce from this process is surprisingly good. So I'm seeing another question coming up in the question box here. Would degumming still be necessary? Well, yes. Generally speaking, you need some level of degumming. I mean, if you're starting off with soybean oil, you could easily have 1,000 parts per million of phosphorus in crude soybean oil, and you want to get that down well into single figures before you could even begin to consider deodorizing it. So, you know, we've often set a limit of 3 parts per million for the phosphorus level in the oil before it goes into the deodorizer. Preferably you'd want lower than that, but I have seen a plant get away with 5 or more, but you certainly couldn't come in with 100. It wouldn't be possible at all. So these are the conditions that we would expect in a deodorizer today. This might be what you would get for deodorizing neutralized soybean oil. So 240 degrees Celsius, 3 millibar, a total of 10 kilograms a ton of steam injection. So it's 10 kilograms of steam per ton of oil. And the batch deodorizer on the previous slide, we had 180, we had 8 millibar, and we had 65 kilograms of steam injection. So this is a much more efficient process. We've also got heat recovery, so that we can partially heat the oil with by cooling the hot deodorized oil. And this can do hundreds, or even you can do hundreds or even thousands of tons a day by these kinds of processes. Now it's important to understand. Oh, that's another question. Is not a phosphorus removal? No. So yes. Oh, I'm guessing the. Oh, I've got more questions. No, degumming was, yeah. So yeah, I'm struggling here to see all of the But yeah, if you in the questions here, it doesn't help. I mean, somebody's asking here, if we used a much higher vacuum, say 0.1 millibar, could we avoid the need to degum the oil? I would say, well, no, I don't think that would be workable. The phospholipids, which which effectively are the gums, they're not very volatile, so you can't really remove them by evaporation. And there's also other reasons why you wouldn't want to go down to such a low deodorizing pressure, because it would be uneconomical to do that. I don't know if you want to join in with a verbal discussion, and have yourself unmuted, then please indicate that. So one of the things you have to understand about deodorizing is the principle established in 1887 by François-Marie Raoult, the French chemist, and this is often known in English as Raoult's law. Now, basically what that says is, if you've got a substance dissolved in another, then it only exerts a vapor pressure proportional to the concentration of that substance. So oleic acid has a vapor pressure when it's pure of 42 millibar, but if it's only present in oil to the level of 2% in that body of oil, then it only exerts a vapor pressure of 2.6 millibar. And what this means is that if you have oil that contains less than approximately 2% fatty acid, and it varies according to the conditions in a fatty acid, but round about that number, then if you heat that up to 250 degrees in a deodorizer, you expose it to a pressure of 2 or 3 millibar, then nothing's going to happen. And the oil is just going to sit there, and nothing's going to boil off. And apart from fatty acid, all of the other components present in oil that we're trying to remove are present in very low levels indeed. So, I mean, some things that we're trying to remove, some of the flavor components, glycidyl esters, they're present in parts per million. And a glycidyl ester at, say, 1 part per million, it's only exerting a vapor pressure in the region of 10 to the minus 4 millibars. So we're looking at trying to remove substances which have a vapor pressure far below the head pressure that it's practical to have inside the deodorizer. So because just heating the oil isn't going to drive off the volatile components, we have to consider removing them by blowing steam through. Now, we often use in this industry what we call the Bailey equation for steam stripping. Now, Alton E. Bailey, who proposed this, is famous for the textbook that bears his name, although he's no longer with us by quite a margin. And what this really says is, if it says that the amount of steam that you use is related to the deodorization pressure, the vapor pressure of a given component, the initial and final concentration of those components, and what we call the vaporization efficiency factor, which can vary between 0 and 1. Now, I'm not going to go into this in detail, but the upshot of it is that in practical terms, the Bailey equation means that the stripping is a function of the volume of steam used. And this is important to remember. It's not really it's not just the pressure, and it's not just the mass of steam used, but it's a combination of those two things that really cause the stripping effect. And if you use half the mass at half the pressure, this has about the same effect as long as you're at constant temperature. when it comes to stripping substances out of the oil, and more of this later. It's also important to remember that the vapor pressure of things like fatty acid and tocopherol and other substances that we're trying to remove approximately doubles for every 15 to 20 degrees C rise in temperature. So if we increase the temperature by 15 or 20 degrees, then the steam required to strip the volatile substances out of the oil is cut by half. So from that point of view, we want to operate the process at as high a temperature as possible. But if we go too high, then we'll start creating what are regarded as contaminants such as trans fatty acids and glycidyl esters, which we want to avoid. So there has to be a compromise between these two effects. Now, we can see it's instructive to look at the Votator deodorizer that was popular between the 1940s and the 1980s. And this was also invented by the Mr. Bailey that we heard about earlier. And it basically consists of a series of batch deodorizers, one on top of the other, used for heating, deodorization, and water cooling. And what's happening here is the oil is just sitting in this box here, which is known as a tray. There are pipes in the bottom of the box, and there are holes in those pipes, and steam is coming out of those holes, and that's deodorizing the oil. And then it falls into this cooling tray, and it's cooled before being discharged. And how this used to work was you typically had a deodorizing time of around 60 minutes, a temperature of at least 250 degrees Celsius, 8 millibar, and 30 kilograms of steam per ton of oil. And then in the 1970s, Votator introduced what they call the mammoth pump, and this is a popular concept in deodorizing today. There's many different versions of it, and also known as a gas lift pump. Now, what happens here is there's a sort of what they call a steam chest, a box with the steam inside. There are holes in the side of the box. Steam comes out of these holes, rises up this tube, oil rushes in to take the place of a steam. You get a mixture of steam and oil rushing up here, hits the deflector plate and deflected back into the oil, and the steam rises up, taking away the volatile material. Now, I wondered for years about this term mammoth pump and whether Votator had actually invented it or not, but it seems they certainly didn't. The mammoth pump was a term used for an airlift pump that was used to draw water out of mines, and the invention is said to date back to 1797. And here's a newspaper article dating from 1906 where the term mammoth pump is clearly used, and certainly Votator didn't invent it. But what we see here is that if you introduce the mammoth pump into the Votator deodorizer, this is what they did. Instead of 60 minutes that they had with just the pipes with holes in, they've got one deodorizing tray, and it's operating on a 15 to 20 minute cycle. So why is that? Now, I thought for years, and maybe you think too, or maybe you don't, that the mammoth pump is more efficient at mixing steam with the oil than just bubbling some oil in through some pipes. But strangely enough, that doesn't seem to be the case. That if you look at the Votator design, and you also look at later designs that came along, like the Smet Unistock and the Kirschfeld deodorizer, where you had just steam pipes involved, or you look at other designs which use mainly mammoth pumps, the way in which the steam is mixed into the oil under industrial conditions, at least, and you may get a different result in the lab, but under industrial conditions, this vaporization efficiency is virtually the same however you mix the oil, steam into the oil. And to me, that seems unlikely. But you know, when I've looked into this and done some measurements in the field, and when people have gone into the lab and tried it as well, it seems that is true. So what is it about mammoth pumps that make them so desirable? So what it means is, if you put 30 kilograms a ton of steam into the oil in a mammoth pump, you can get all the oil, all the steam into the oil in only 15 minutes. And because you've got this huge surging oil coming up here, but it's immediately deflected back. So all of the impact of the oil going upwards is deflected back downwards. But if you put the same amount of steam into a tray with steam injection pipes there, it just all bubbles up and overflows. And this deodorizer had these boxes, these square boxes inside a cylindrical column, so it would actually fall down to the bottom of the column, and you'd have a terrible mess. So when Votator moved from trays with steam injection pipes, or sparge pipes as we sometimes call them, they didn't change the amount of steam that they were putting in. They just used the same amount of steam, but in a shorter time. And what you sometimes see today is you'll see mammoth pumps and sparge pipes, injection pipes used together. This is a picture showing it happening. There's the steam coming in. This is the hat or deflector plate. Here's the oil being deflected off the top of the hat, and this is oil that's being agitated by these pipes below. Now here's a myth that I think you must avoid. It's often been said that if you have this arrangement, the steam should be split 50-50 between the mammoth pump and the injection pipes. Now, we've only just been hearing that a mammoth pump can put more steam into the oil in an injection pipe. So it doesn't make any sense to make these two the same. You can put far more steam into here than you can into here. So I'm crossing that out. Don't do that. And this is what will happen if you try to put an equal amount of steam into the pipes as you do into the pumps. Then you'll just get a whole load of froth appearing on the surface like this. All of this will be just a mass of bubbles, and the way the oil is being deflected off this deflector plate will be disturbed. So what I suggest you do instead is you fix the amount of steam going in at this point, maybe a maximum, absolute maximum 2 kilograms an hour per square meter of oil surface area, and then whatever other steam you need to put in here into the pumps. And if you want to adjust the flow of steam to the deodorizer because you want more stripping or less stripping, then this rate should be kept the same. The amount of steam you're putting into what we call the non-deodorizing trays, the heat transfer and buffer trays, that can be kept the same, and only adjust this number here. It's often common to talk about deodorizing steam in terms of a total amount of steam being injected into a deodorizer. So in this case, we've got 10 kilograms a ton of steam being injected into the oil of the deodorizer. But it's important to remember that not all of that has the full deodorizing effect. So here we have deodorizing steam in the deodorizing tray is 8 kilos a ton, and the heat transfer and buffer trays, we've got 2 kilograms a ton, and that's a realistic sort of rate. But this 2 kilograms a ton isn't having the same stripping effect as one of these 8 kilograms a ton, because this tray, for example, is well below the deodorizing temperature. This tray is well below the deodorizing temperature, so is this one. This one is getting close to the deodorizing temperature, so you might have some effect there. So, but you can't expect all of this 10 kilos to have the same effect as this 8 kilos. So, and different types of deodorizer require different amounts of steam into the non-deodorizing tray. So if you have a semi-continuous deodorizer, such as the Votator or one of the more recent designs, easily have 2 to 4 kilos of steam per ton of oil. In a continuous deodorizer, where the heat recovery is in a more compact way, perhaps 1 to 2 kilograms a ton. So what we have to say from that is that the total steam flow to a deodorizer is only an approximate guide to the intensity of deodorization. You really have to also consider how much steam is entering just the deodorizing trays. Now, if you look at a set of heating coils that you might have in, say, like some kind of semi-continuous deodorizer, the Votator deodorizer, the Desmet multi-stock, and a number of others that are available. If you have a steam pipe just going around below these coils and you don't turn it on, there's no steam injection at all, then the heat transfer rate is very, very low. If you put just a tiny little bit of steam in, it jumps up very quickly. And then as you add more and more steam, the heat transfer rate steadily increases until it gets to a point where it doesn't increase anymore, and you can put as much steam as you like into that tray from then on, and you won't get any more heat transfer. So it's important to recognize where that point is, and you might have to do some experiments to find it. Because if you put more steam, if you're over here and you're putting more steam in than you need to, that steam you could be using for deodorizing. And if you could, by adjusting the rate of steam to all your non-deodorizing trays, you could get 10% more steam into the deodorizing trays, then I mean you could do 10% more deodorizing, and that could be really very significant. Also, it's worth remembering that if you have a continuous continuous deodorizer with bleached oil flowing in pipes and deodorized oil flowing in baths, if you put too much agitation steam into that system, you can disrupt the plug flow. So by making this, instead of a plug flow bath, you make it a mixed bath, then you don't get any improvement in the heat recovery. In fact, it drags the heat recovery down. So by adding more steam, you've actually pulled down the heat recovery. So definitely something to avoid. Now, some deodorizer designs actually have a coil inside a gas lift pump. And the idea of this is that you blow steam inside here, oil and steam flow up across the coil, the oil is deflected back into the bath, and of course the steam goes out like this. And the idea of doing this is to improve the heat transfer. And you think, well, that sounds sort of reasonable. I could sort of believe that might work, but I have actually had the opportunity to I'm just checking the questions here. Deodorized lecithin using steam, of course. Well, yeah, perhaps we'll cover the matter of lecithin later. I mean, basically, if you dry lecithin, some of the impurities are carried away with the steam as part of a drying process. So that's really something. You're certainly not deodorizing lecithin in anything like the equipment we're talking about here. So what's happening here is that the oil is being dragged through across this coil, but I have had the opportunity to measure the heat transfer rate in this kind of system, and it's virtually the same as if you had the coils like this, just in an open bath with a sparge ring below them. So this looks encouraging, and you know, it's hard to believe it doesn't work better than it does, but certainly the evidence I've seen suggests it's no better than just having open coils. But we've used 3 times the steam rate to do it, which is unfortunate. So if you look at the example we had earlier, that there are 2 kilograms a ton of steam in the non-deodorizing trays, 8 kilograms of steam in the deodorizing trays, then if we then say, well, we need, with this coil in the gas lift pump, we need 6 kilograms a ton of steam for the heat transfer and buffer trays. The total steam goes up to 14 kilograms a ton. So we've needed a 40% increase in the energy required for the total steam and the vacuum energy. Now, I'm going to say this is a myth, and not everyone will agree with me here, so I have to perhaps tread carefully. You don't actually need a very low pressure to get good deodorizing. So it's saying it's a myth that a very low deodorizing pressure is essential for good deodorizing. And the Bailey equation has already told us that the volume of steam rather than the operating pressure, it's essential to have the volume of steam, not so important to have a low deodorizing pressure. In fact, even in the early 20th century, we can see that sometimes deodorization was done under atmospheric pressure, and theoretically that's okay, but practically it's hopeless because it's massively expensive and you need vast quantities of steam compared to doing it under vacuum. But the theory of the Bailey equation says, well, yes, you can deodorize atmospheric pressure, but we don't recommend it. So the message here, another question's appeared. No, I don't see it here. Mammoth pumps require higher, so we're getting a question here. Mammoth pumps require higher bed heights, which diminish the efficiency of sparging steam. What does it mean? What more efficient to use lower bed heights with only sparging steam? Well, you might think so, but when you actually try, I mean, it's very sort of intuitively you think that's the case, that if you had a shallow deodorizing tray, that would be more efficient than having this very deep bed with the Mammoth pump in it. But when you actually try it, and maybe if you had very, very sensitive measurements, you'd see a difference. But in practical terms in industry, I can't see any difference that creates. So what we have here is that we have 3 millibar with 10 kilograms of steam. I'm going to say that in terms of the stripping of the oil and the quality of the oil that you're going to get, you do just as well if you had about 20 kilograms a ton of steam. And in the 80s and 90s, nobody thought there was any problem with that at all. I'm having another question here. Seems that once a given heat transfer is achieved by convection steam agitation, then the heat transfer is controlled by heat conduction related to the coil's geometry. Well, yeah, I mean, once you get to a certain amount of steam agitation, you can't take it any further. Oh, there's more appearing here. Yeah, related to this. Yeah, and the coil geometry does have some effect on this. Obviously, the metal itself has got a very high heat transfer rate, but if you have the coils packed too close together, or maybe have a U-tube bundle with very, very tight spacing between the pipes, then that can restrict heat transfer, and we have seen that occurring as a problem. But it's certainly quite clear, a lot of people have observed this, that there is a limit to the amount of steam agitation you can do, and once you've reached the maximum level, you can't go any further, no matter how much steam you put in. And someone's saying nowadays Desmet provide a tray more than 2.5 meters height in one tray, with the statement that they especially designed steam pump gives the same effect of the old deodorizer 1 meter height. Well, yeah, I think that's valid. In fact, some of the old batch deodorizers had very deep tray, very deep tanks in which the oil was in, and so long as you've moved all the oil, you've got the pump working quickly enough that it's turning the oil over several times during the time it's there, then you're still going to get the same effect. I mean, you might say that, well, there might be a very small marginal effect if you had a very large deodorizer and a lot of pumps. You can say, well, theoretically there is a marginal effect, but basically, if you put a kilogram of steam into the oil, it's going to have the same effect. Desmet has removed even the splash oil collection, and it drips into the final tray, and they claim this does not affect the quality of the final product. Is that true? Well, yes, I would support that, although I'm now retired, of course. But basically, I don't have it on this particular slides here, but basically what you're doing is any splash oil any splash oil above, we're talking about the multi-stock deodorizer now, any splash oil above the first deodorizing tray falls into the first deodorizing tray. Any splash oil from the first deodorizing tray is deflected back into that tray, and any splash oil from a second deodorizing tray, okay, that could possibly, some of that could possibly fall down to the bottom of the deodorizer, but in fact it's basically deodorized oil, and probably as it's falling down there, it's got steam coming up, and it's further deodorized as it goes on. And there's, Desmet built a lot of deodorizers without the splash oil tank, and as far as I'm concerned, that's never caused any problem.
Hey, Alan, I'm sorry. I think I missed a question before. Andy
Yeah,
Carlson had
I'm
asked.
only getting a small window. I'm only getting sort of one-liners
Yeah,
here, and then I have to sort of open them up.
same.
Yes, all right. So,
I can see
it's
Andy
hard to
Carlson is
study all the
asking.
questions while doing the presentation at the same time. So
Yeah.
yes, please.
Does excess steam result in FFA revision / rise?
Well, I mean, if you put a lot of steam into the oil, you can, or at a very high temperature, you can actually start to hydrolyze the oil to break it up into free fatty acid, and a certain amount of that is going to always happen. But if you look at the amount of fatty acid you've recovered in the vapor scrubber, and you look at how much you removed from the oil, there's always a bit more you've recovered than you removed, and it's all a matter of trying to limit that. It'll never be zero, but certainly there, in any situation, there's always going to be a certain amount of oil that's turned into fatty acid. This might be an argument for why you want to use a lower pressure. That at a higher pressure, although you've done the same amount of stripping at say 6 millibar as 3 millibar, at 3 millibar you might get slightly less hydrolyzation, slightly less creation of free fatty acid, and that might be an argument for why it would be better to operate at a lower deodorizing pressure. But on the other hand, there's an argument that says you can remove color, that the steam actually reacts with coloring bodies in the oil. Certainly some people have said this, and so having a higher mass flow rate of steam helps to reduce color. And there's also an issue, if you go down very, very low in pressure, then condensing the volatile substances in the scrubber starts to become an issue. But certainly you will always get at least some small degree of hydrolyzation, creation of fatty acid in the deodorizer. You have to try and minimize that by using the lowest possible temperature, making sure the steam is very dry when it goes in, because if you introduce droplets of water, that will certainly have a negative effect on that. Okay, shall I carry on?
Around there. Got a lot of questions in here.
Yeah, so I'm only getting a sort of the preview here is yeah, if you can perhaps read these out, because the preview here is I'm only getting a sort of not seeing them very easily here. So
Pull out the box a little bit.
oh yeah, so is there any chance of more oil loss with higher temperature from Gosh? So yeah, there is. Yeah, I think that's true, that there is, you're more likely to create fatty acid and have that stripped off, excess fatty acid, and strip that off at higher temperatures. And the other thing with higher temperatures is that you can generally increase the losses. So if you do more deodorizing, you put more steam in, more temperature, more vacuum than you need, is going to lead to more losses, either from fatty acid or from other things you didn't want to remove. So, you know, if at the end of the day, instead of the distillate being 0.3% of the oil flow, it's 0.4% of the oil flow, that's 0.1% that you aren't selling as oil. Now, maybe you can sell it as distillate, but you know, whether you're getting getting an enough extra margin out of selling the distillate, that's perhaps a bit questionable. So yeah, it is all a compromise. You want the highest temperature possible that will reduce the steam flow and cut down the color, because a high temperature will reduce the oil color. So yeah, it's all life's a compromise, unfortunately, and there's no absolutely final result you could say, well, yeah, that's absolutely the perfect temperature. Depends really on what your priorities are and where you might get to. So effect of structure. Oh, let's see, effect on structured packing here.
I think we had one earlier as well, saying, "Dear Dr. Paine, thanks for a lot of your great presentation. Taking into consideration the problems of glycidyl and MCPD esters, how do you evaluate the perspectives of replacing deodorization by low temperature techniques?" Example,
well,
using
3-MCPDs are formed at quite low temperatures, well below, I think, something like 140 degrees Celsius, so well below a practical deodorizing temperature. Glycidyl esters are kind of a bit interesting, because they're formed more rapidly, a bit like trans really. They form more rapidly as you go at higher temperatures, but they can also be removed. So if you get the right balance between the amount of stripping steam and the time and the temperature and everything, then you can actually beat the formation, if you like. So you can take them away more quickly than they can form. But there's a whole subject in itself, and perhaps we won't sort of get into that at the moment. But yeah, it's certainly an issue, and it's being better and better understood, and you can strip glycidyl esters more quickly than they're formed under the right circumstances. So what's this is, they're a deodorizer that has a preheating vessel that heats the oil to 250, 260 over a period of 3 hours. Well, that's quite a long time. This heated oil is then transferred to another main stripping column. Will this not develop TFA, trans fatty acid? Well, yes. I mean, if the heating tray is taking 3 hours, then certainly there's plenty of time to form trans fatty acids. I mean, at 260 degrees Celsius, soybean oil will form about 3% trans in an hour. So 3 hours at 250. Well, I mean, yeah, so it's not at that temperature for the whole 3 hours, but it's likely that maybe half of that time at least you've got the oil at a very high temperature. So yeah, that would be I would say that was an excessively long period of time to spend heating the oil. And yeah, I would definitely expect some trans fatty acids to be formed during that process. What is the source of chloride to form 3-MCPD? There's a question here from Sang Kang. Well, it can come from many. One of the sources is bleaching earth that has been activated with hydrochloric acid, with hydrochloric acid. So you want to avoid that. But you know, chloride, it's in the water, it's in the fertilizer, it's in the steam used for processing the fruits in the mill, various sources, and there's a lot of work going on to try and cut down the exposure to chloride. But you know, there's chloride all around us, it's in the soil, and it's impossible to avoid at least a certain amount of chloride entering the palm as it's growing. So I'll move on here now. If you have a situation where you're putting 10 kilos of a ton of steam into the oil, and you've designed for 3 millibar, but all of a sudden you get 6 because there's been an air leak or something like that, then obviously you won't get good deodorizing. So from this point of view, a low pressure is important for deodorizing. But in this situation, you can't increase the sparge steam, the injection steam, to 20 kilograms a ton because the vacuum set hasn't been designed for it. So here are sort of some principles I want to just summarize here. That if you have a rise in pressure above the design level, then you're going to get an adverse effect on deodorizer performance. But if you have a higher design pressure combined with a proportionally higher steam flow, then you'll get the same stripping performance. And what pressure you choose is driven by the economics of the process. Now, in deodorization, there's 2 commonly used forms of the vacuum system. There are vacuum systems based on steam jet ejectors with intermediate condensers, and these condensers can use either cooling tower or chilled water. And they're also known as sublimating systems, where the steam freezes on the outside of tubes, which are maintained at around -30 degrees Celsius, usually by liquid ammonia. And then you have a small ejector set, or sometimes some dry pumps, to remove the rest of the material, the non-condensables. And if you study all of this, what happens is that the amount of steam required to deodorize oil falls as the pressure falls, as we've already discussed. But the amount of energy required to create the vacuum rises per kilogram of deodorizing steam. And it's the balance between these 2 effects that ends up with the most economical operation. And in this case, in this top line, this shows what happens when you have a system using cooling water. The ideal deodorizer operating pressure is around 3 millibar, but if you go a little bit either side of that, it doesn't really make very much difference. Again, the same thing more or less with the chilled water. Again, if you go either side of 3 millibar by at least half a millibar, it doesn't really make any difference. And the sublimators, they're at their most optimum operation at about 2 millibar. And again, within a small range, it's not very sensitive. So it's important to remember that, to observe here, that whatever pressure you choose, the sublimator is always going to be the most economical in terms of running costs. So really, what I'd like to say is that the oil quality isn't directly linked to the operating pressure. So there's no need to go below the most economical operating pressure. So in the case of ejectors, around 3 millibar. In the case of sublimators, around 2 millibar. And the most important reason for using sublimators instead of ejector set is an economic reason. It's much more economical in terms of running costs. Okay, sublimators are more expensive to buy, but in the long run, when we talk about years now, they're much more economical. So just a quick summary, and then we can take some more questions. First of all, perhaps we ought to remember that oil processing isn't a new industry. It goes back hundreds, maybe even thousands of years. Steam volume is the key factor for steam stripping. And mammoth pumps can inject more steam into the oil than steam injection pipes. The total amount of steam that we put into a deodorizer varies according to the deodorizer configuration, because some types of deodorizers require more steam than others for the non-deodorizing trays. And a low deodorizing pressure isn't essential for good deodorizing, but it's useful to select a low operating pressure because that's the most economical thing to do. And depending on the type of vacuum system, that most economical pressure varies between about 2 and 3 millibar. So that's all. Thank you very much. And if there's more questions or a few that I haven't answered yet, then please fire away. Is it possible to get slides of this? I think there will be some. Yeah, would it be possible to get slides of this interesting presentation? If yes, by which way? Thanks a lot. Now I think this is going to be eventually posted on the AOCS website, isn't it, Amy?
It will, and if you send me your slides, I can also include a link for people to download with the recording, as well as put them on Inform Connect, if that's helpful.
Yeah, I have made some notes with these slides. So now I haven't, what I've done in some other previous case, I made like a full speaking script. Now in this case, it's not like a full script, but it's just sort of guide notes and various things. So what I'll do is I'll make a PDF with the notes pages, which will show some additional information to what's on the slide and some explanatory notes. But it won't be like a transcript of what I've said, because also we've been interjecting with questions and other things at the same time.
Yeah, we can absolutely provide that. And if anyone has questions, you can of course use the question box. But if you would also like to be unmuted to join the conversation,
Yeah,
you can use the
there we haven't had anybody do how to. Oh, right.
Yeah, I think there were probably a few questions
No,
missed that you guys wanted to.
Fill in the Bertavale. That's an interesting question. So how do we know what the well, really you have to know this by oh, there's quite a few questions appearing here. So yeah, the site, yeah, we've had that.
And you can undock the question box and expand it. It makes things much easier.
Yeah, I've got a sort of expansion below the question. Oh, here it is. Is nitrogen blanketing used in deodorization? Well, not as, I mean, there was once an idea, in fact, it comes up from time to time, to use nitrogen instead of steam for deodorization. But you know, the economics of it don't seem to work very well, and theoretically it doesn't. Of course, it doesn't create hydrolyzation, but there's still, it's an idea that never really got off the ground. People have tried it, and well, it was too troublesome to use. So, but obviously, nitrogen blanketing is often used after the oil has been stored. So, what commonly have in a deodorizer, you have a nitrogen injection point, where the oil is saturated with nitrogen, goes into the tank. Some of the nitrogen comes off and starts to fill the atmosphere of a tank, and you can also introduce nitrogen deliberately as a blanketing on the top of the tank. And what have we got? Is it important to have different deodorizing steps for different types of oil? Well, yeah, I know you can often have different deodorizing conditions for different things. I mean, for instance, palm oil, it's very common to deodorize palm oil at 260 degrees Celsius to remove color. Now that's starting to have an impact on things like glycidyl esters, but people are still doing it with some other types of oil, like lauric oils, like coconut oil. The volatile components you're trying to remove are much more volatile than with other oils. So from that point of view, you might only operate at 220, 230 degrees Celsius. And where you have a stock change deodorizer, you get many different oil coming down the column one after the other. It's common to keep the sparge steam rate the same, the vacuum rate the same, but to adjust the temperature according to the type of oil that's coming along. Right, thanks. And then how do we know? How do we know the vaporization efficiency to fill in the Bailey equation? Well, I mean, really, there's maybe it's possible with some kind of clever simulation to predict it, but what I've done is I've gone out into the field and tried to measure it, looked at how much steam we're using. For a palm oil physical refining, for example, you'll get something like 0.45 to 0.5 for neutralization of something like soybean oil, maybe 0.25, something like that. If you've got oil that's starting off around the 0.1, 0.2 FFA, maybe at 0.35. So yeah, something between, if you said, well, palm oil at 5% is 0.5, neutralized oil at 0.1 or so, maybe that's 0.25, and then something in between for these other cases. So it's not easy to know, and really you have to rely on experience to work that out. What else have I got here? Is this quantity of steam proportional to the FFA or other volatile? Well, yeah. I mean, to a certain extent. I mean, I think what people do in deodorizing, they're measuring the amount of free fatty acid in the oil, and that is important because you've got to remove free fatty acid because it can contribute to the smoke point of the oil. But it's also like a benchmark, I think, to how much of these other substances you're going to remove. So if you've reduced the free fatty acid level by, let's say, 10 times, you've gone from 0.1 to 0.01 or 0.2 to 0.02, something like that. It also indicates that you've removed these other materials as well, and it's not that you could say it's proportional, because what the Bailey equation is talking about is the ratio between the starting and the finishing levels of the fatty acid or other materials. So if you start off with palm oil that's at 5% free fatty acid and you go down to 0.05%, that's a ratio of 100. And if you're starting with soybean oil at 0.1 and you're going down to 0.025, that's a ratio of 4. So if you're doing a ratio of 100, you're obviously more extreme conditions than a ratio of 4. But it's this ratio of concentration that's important, not the actual level of the fatty acid itself. Oh, what?
And I saw the hand raised, but twice. But by the time I could get to look to see who it was, they'd unraised it. So if you are trying to raise your hand, if you'll leave the button on or not double click it, you just I
Yeah, if anyone
will.
would like to join in verbally, then all that's fine. But I'll continue to answer these questions in the question box. What are the parameters to judge if you have optimal deodorized oil? I mean, first of all, you're looking at the fatty acid level that you're targeting to go down to. That's always an important factor. Color is often seen as very important. Have you made too many trans fatty acids? Have you, these days even, have you made too much glycidyl esters? And a lot of people haven't got the facility in house to do that yet, but you know, I think that's all. There's a hand going up, and it's disappeared again.
Yeah.
So yeah, so and of course you'll have a tasting panel. People who are experienced at tasting oil will taste it and judge whether it was the right quality or not. So these are the main things, I think, of the fatty acid level, the taste, and the color. And then these supplementary things like trans and glycidyl esters may come into the picture, depending on what kind of situation you're in. Oh, color reversion. Color reversion. How do deodorizer temp and pressure impact to it happening? Well, yeah, you can get color reversion, you can get flavor reversion, you can sometimes get free fatty acid rising. It's difficult to know what's going on there. Very often, you know, reversion can be an effect of bleaching. There's certainly been some studies done to show that different levels of bleaching will result in different levels of stability in the oil once it comes out of a deodorizer. So the deodorizer isn't entirely responsible for that, but it is important in deodorizing to heat treat the oil for sufficient time to make sure it's stabilized. So if you're operating at maybe 250 or 260 degrees Celsius, then maybe 15 minutes might be enough. And if you're operating at 240 degrees Celsius, then perhaps you need 25 minutes. And if it's at 230, maybe 40 minutes. So as you go down in temperature, you need more and more time to make sure the oil has been properly stabilized. It's one of these multi effects. I don't think it's just one thing that is causing that to happen. So you do need to treat the oil with a certain level of temperature for a certain amount of time to stabilize it. But once you get beyond that, there are other factors such as the original quality of the oil, how it's been treated in bleaching, and also how it's been stored afterwards. This can also be an issue. Have you got the phosphorus level down sufficiently? It's quite a complicated issue. What's the best temperature to add citric acid after deodorization? Well, it's anything below about 150. You can add citric acid inside the deodorizer up to about 150, perhaps in the range of 100 to 150 degrees Celsius. If you're talking about adding citric acid after deodorization, it's probably best to add it, assuming it's coming out of a deodorizer, below 150 degrees Celsius. It's probably best to add it as soon as possible. But I think generally speaking, if you can add citric acid into the deodorizer itself, but below a temperature of 150, I'd say that would be the better thing to do. What's the proper temperature of steam injected into the oil? Well, there's a lot of talk about whether steam should be superheated or not when it enters the oil. So if you look at sparge steam that might be coming on at 3 bar gauge, which has a saturation temperature of 145 degrees Celsius or something like that, it would be normal to expect that to be superheated to maybe 180 or 200. And in fact, what happens is if you take some 10 bar steam, you dry it as much as you can, knocking out all the droplets, and then you reduce it down to 3 bar to use that 3 bar steam to do the sparging, then it will be already automatically superheated. So, and then it'll be at like 180, and the saturation temperature of the steam will be 140 something. So you've already got some kind of automatic steam superheating there. So I don't think it's necessary to heat the steam up to the temperature of the oil, because when the steam enters the oil, the amount of energy required that the steam takes from the oil to raise it up to the deodorizing temperature is very, very small. So it's only dragging down the temperature of the oil by a very small amount. So if the steam comes in 180 and it enters the oil and it's heated to 250 by its interaction with the oil, that's taking away a very small amount of heat from the oil. So the important thing is to make sure the steam is superheated, that it's dry, but as long as you achieve those conditions, whether it's 180 or 200 or 220, to my mind, doesn't really have any effect. And I mean, I worked with deodorizers for something like 15 years before I even encountered a steam superheater. And people have often told me they put steam superheaters into systems and then they've broken down and they haven't noticed any difference. So, I think as long as you make sure it's superheated to some degree or other, and there's no water droplets, then you're fine. You're talking about history of deodorant. What can you say about material construction, considering in the past that they considered using carbon steel? Well, certainly what Votata used to do, they used to make the outer shell of the deodorizer in carbon steel, but the inner boxes, the trays, were made out of stainless steel, or I think in some early examples might even be made of just a pure nickel, which sounds elaborate. And certainly the old batch deodorizers, which operated at a lower temperature than is common today, they were commonly made of carbon steel. And iron, if you get a significant amount of iron pickup into the oil, it can act as an oxidation promoter. So that's something to be avoided. And adding citric acid to the oil, what really citric acid is doing, it's joining or chelating, as they call it, any metal ions present, particularly like iron, copper. Copper is a very high catalyzer of oxidation in oil. And so, yeah, certainly they got away with using carbon steel with lower temperatures of 180, 190, but today certainly stainless steel all the way. And what we have, what oil parameters should be considered? What the oil parameter? I'm not quite sure what that's. What was it? Could you from Akash Honrao? You perhaps yeah, so I don't know whether you can just add to that, Akash, what you mean by what oil parameters should be considered to design a deal. I mean, yeah, there's many things you have to consider. Really, you've got to consider what oil have you got, and because usually you're starting from, I've got some oil that I want to deodorize, and so you're going to look at how much oil you've got, what are the level of free fatty acid you're trying to remove, what are the limitations on the formation of trans or glycerol esters. Do you want to remove a certain amount of color, or is it for a purpose where color really doesn't matter? And there are some cases where color doesn't really matter. So yeah, it's quite a broad brush question. If you want to add some, add some more to that because you have a particular thing in mind, and then please feel free to either come on vocally or write another question. What should the ppm be for citric acid? Up to about 50 parts per million of acid on a dry basis, although that's probably a little extreme. Probably 25 parts per million usually does the job. And it's important to remember that citric acid by itself isn't an antioxidant. What citric acid does is it reacts with any metal ions as present, effectively neutralizes their effect as oxidizing agents. But if there are no metals there at all, if you've got totally pure oil, then adding citric acid doesn't really help you. Oh, we've got some thanks here. Great job, it says. That's nice to hear. Do you believe the quality of deodorized oil is the same by stripper base versus tray deodorizing technology? So stripper is much more economical. Well, yes, this is right, that if you interact oil with steam through a stripping column in a countercurrent stripping, so the oil's coming down and the steam's rising up, that is using about half the steam to strip the volatile components out of the oil as you need in just a tray deodorizer. And as we've already said, you need a certain amount of time in which to deodorize the oil. So just stripping the volatiles out in a stripping column, which might only take a minute or two, that's not usually enough to fully treat the oil. So you then have to hold the oil in a deodorizing tray below the stripping column in order to fully treat the oil. Now it's there are other things to bear in mind. I mean, in the palm oil industry, the use of stripping columns is very common, and part of the reason for that is that palm oil is less easily oxidized than say soybean oil, which is and because soybean oil is very easily oxidized, and a stripping column has a very high surface area, some people are a little bit reluctant to use it for these very easily oxidized oils. So in a lot of cases, people have been a little hesitant to use them in soybean or canola or sunflower, even though they are very effective, and there's a good argument for using it. Some people are sort of just held back from doing that. But in terms of quality of a deodorized oil, once you've stripped away the volatile components and then you've held them in a deodorizing tray for the requisite amount of time, there's no reason why you can't get just as good a quality oil in terms of flavor and stability as you could by any other means. Oh, thank you. The temperature of the oil. The temperature of oil should be 240, or the thermal use oil temperature should be. I think so. This is a question. The temperature of the oil should be 240 degrees C, or the thermal use oil, the temperature should be. So what I think this is saying is talking about heating oil using organic thermal heat transfer fluids. So what I'm talking about is typically, and I say there's a range of temperatures you can use, but a typical temperature for deodorizing oil, say neutralized oil, would be around 240 degrees Celsius, and the temperature of the steam or thermal fluid that you're using to create that temperature would be higher still. And 240 would be quite a low temperature for thermal fluid heating. That could easily, I mean, you could easily have organic thermal fluids operating close to 300 degrees Celsius. The high temperature, low pressure combination can lead to higher oil contents carried away with the steam vapor velocity. Well, not really. I mean, the point I'm trying to make here is that you get the same amount of stripping for the same amount of volume of steam. So if you have a deodorizer that's in all cases identical, and you say put 10 kilos of steam in at 3 millibar, or you put 20 kilos of steam in at 6 millibar to get the same stripping effect, that's creating the same volume, and that's the same velocity inside the other piece of equipment. And the reason you might use the lower pressure, to operate at 6 millibar rather than, to operate at 3 millibar rather than 6 millibar, is because it's more economical to do it. But the volume of steam and the velocity of the vapors, assuming everything else is the same, that's also the same, because it's the volume of steam that's the main driver in the process. What can you say about heating and cooling under vacuum compared to under pressure? Well, yeah, this is definitely important, that particularly the cooling of the oil under vacuum. When oil comes out of deodorizing trays, it's normal to agitate that oil during the heat recovery, during the cooling or heat recovery, down to maybe around 140 degrees Celsius. And if you take the oil, let's say 250, and you directly put that into a closed heat exchanger to cool it down, this can definitely generate some off flavors. This is a well-known, this is been well tested in. What are the highest cost elements in the deodorizing process? Well, heating the oil, even with high levels of heat recovery, the heating of the oil can still, certainly in terms of energy, is still a very large part of it. The other big energy user is the vacuum equipment. We made a lot of progress in bringing down the operating cost of vacuum equipment, as you'll have seen in the various graphs that we've shown. But in fact, there's still some progress to be made with the heating costs. So, I mean, the cost of heating the oil, it can be hundreds of thousands of dollars a year in a moderate size unit. Effect of structural packing versus mammoth pump, which is more effective? Well, as I said, that in a tray deodorizer, whether you have a mammoth pump or you have sparge pipes, steam injection pipes, it's the same efficiency. But structural packing is roughly twice as efficient as anything you can do in a tray deodorizer. So if in a palm oil physical refining, you need a total of maybe 10 kilos a ton or so, you can perhaps get away with 5 kilos a ton or less if you include some structural packing into the system. What are your thoughts on soft deodorization movement to remove the amount of good stuff that is removed along with the undesirables? Well, yeah, it's what you say was, soft deodorizing is a kind of catchphrase, if you like, but it is important to only do what you need to do. So if you're going to if you're deodorizing some oil and you've got a particular target, you want to get down to a certain level of free fatty acid or a certain level of flavor or whatever it is, only do as much as you need to do. So don't turn up the wick and have the steam blasting through and take the oil down to a much lower level of components than you need to remove. So yeah, it is. I think it's always been important to do that, and particularly if you look at people who are doing canola or rapeseed refining, they're keen to keep tocopherol in the oil, a natural antioxidant, because the level of the tocopherol in the oil to start with is not all that high. So there's a definite desire to keep that stuff in the oil In soybean oil, you're starting off with like double the amount of tocopherol in the first place. So in that case, there's very often an urge to take away as much as possible. Is there any? I can't actually see how many more questions we've got here. Can you see how many more questions there are, Lorraine? So I'm looking one here. Is it possible to do flashing without steam, just with the effect of deeper vacuum with a reboiler effect to maintain the temperature of the oil by recirculating the flash vessel? Well, if you're asking there, is it possible to avoid the use of stripping steam? I'd say, well, not really, unless you go down to outstandingly low pressures. I mean, some people have tried to do for specialized products what they call molecular distillation or short path distillation, where you're operating at very, very low pressures indeed, you know, orders of magnitude below what we do here. But in a practical deodorizer operating anything like the conditions we're used to operating at, it's essential to add stripping steam to remove the volatile components. They won't come out just by stirring the oil around a heat exchanger or something like that. You can get quite a lot of fatty acid out that way, but the other minor components, they'll just sit there. What is the minimum temperature you can go to so as to decrease the amount the 3 MCPD and GE removed? Well, really, 3 MCPD formation is pretty well independent of deodorizing conditions. It's not totally, but it's not very much affected by deodorizing conditions. GE production, if you can keep below about 230 degrees Celsius, then the rate of GE production is reduced. Now it depends on the nature of the oil, of course. And what is also happening, I mean, you know, this is a whole subject in itself, and I think Veronique Guimond did a presentation about 3-MCPD and G mitigation a little while ago, so perhaps I want to refer you to that. But you can also, if you choose to, you can deodorize the oil at, if you like, full conditions, you know, just as you normally would. And we're talking about mainly about palm oil here. And then you can post bleach it, and bleaching it afterwards will remove the glycerol ester, and then you need a light deodorizing after that to restore the oil to a proper temperature, proper flavor. But yeah, 230, you can often get away with deodorizing the oil and not making very much GE at the same time. Why would the fatty acid increase in it? Well, no, I don't think well, it says a question here, why would the fatty acid increase in the deodorizer? From Nelson Mendoza. Well, usually it doesn't. I mean, what happens is sometimes the steam will react with the oil, the triglyceride, and will break off one of the fatty acid chains and increase the amount of free fatty acid present. But usually what happens is that, you know, that fatty acid that's formed is removed. So the ultimate result is that you start off with a certain amount of fatty acid, and it definitely goes down during deodorization. The exception to that is corn oil. If you deodorize corn oil at higher than, I don't know, about 230 degrees C or so, then it can form some kind of non-volatile acid. I'm not entirely sure what's going on there. It's not necessarily fatty acid, but of course when you analyze it, the analysis is just looking at acidity. So any acidity that's formed is interpreted by the formula as fatty acid, even though it's probably not actually fatty acid present. Now I see that seems to be the last of the questions that I can see here. And Nelson says, thank you. Oh, that's good. Thank you. Thanks very much, Nelson. So, Lorraine, Amy, I don't know whether, are we going to call it a day now, because there don't seem to be any more questions. No one seems to want to come on to chat with me, but never mind. It's been good having these questions anyway.
Yeah, no, this was great. Thank you, Alan, for not only the presentation, but your willingness to answer so many questions and interact with this audience. And thank you to the audience as well for getting involved and asking your questions. I think this was a fantastic opportunity. And so we can call it a day with that. Again, thank you everybody for joining us. Thank you, Alan, for presenting. And thank you, Arain, for yet again moderating for us. You always do a fantastic job. So with that, I wish everyone well, and I will close the webinar.
Okay, thanks so much, Amy. Thanks, Lorraine. Thanks to everybody. Thanks all for your questions. If I haven't answered them all, please forgive me.